So the 4D problems all relate to overcoming friction, and there's not a whole lot notes-wise to say about them. Basically, what this slide is saying, and what you're going to see very shortly, is, we've been using coefficients of static and kinetic friction to figure out forces. But if we think back to the fact that we're actually doing sums of forces on each axis in every situation, now what we're going to use those coefficient of friction equations for is basically to generate more expressions. So in essence, for every single problem, you're going to have 3 different equations that you're able to manipulate to create expressions for components of motion and substitute back in. Doesn't that sound like fun? Okay, so I like spending the time on the friction and forces lab and then going right into 4D because I think it preps you well. As we do these 4D problems, the things to consider every single time: start with a picture and start with a sum of forces. You cannot do these problems without a picture. I should say start with a free body and a sum of forces. Make sure you're accounting for every single force and you're accounting for it correctly. Make sure that if something's on flat ground, you're showing it on flat ground. If it's on a slope, you're showing it on a slope. If force is being applied at an angle, you're showing it applied at that angle. So make sure that you've accounted for the forces. If there are forces that are vectors, make sure you're breaking them down and resolving them. And by now you guys should all be rock stars at this. Never assume that normal force is just negative Fg. You're seeing that again and again and again. Normal force changes based on, based on applied forces, based on slopes. So there are a lot of cases in which normal force is not just the negative of gravity. In general, it opposes gravity, but it's not always equal in magnitude and opposite to gravity. Okay, so we're told that a student's moving a box of books. They have this box, they've tied a rope to it, and they're pulling with a force of 90 newtons at 30 degrees above the horizontal. They actually drew you a picture, but I've drawn it here for you. We're given the mass of the box of books, 20 kilograms, and we're given the coefficient of kinetic friction between the box and the sidewalk. What they want to know is the acceleration. So this is sort of new territory for us, in that now we're being asked to consider the F equals ma component. So early on, you're just resolving forces to get a net force, or a sum of forces. Then you start looking at that sum of forces, the net force is equal to ma. Then we introduce friction. Now we're going to put all 3 of those together, and this is why this is more challenging, because you're going to put all 3 of those together to find mass, to find acceleration, using the expressions that you're creating from your sums of forces on each axis and from your expressions for coefficient of friction. All right, let's get all our forces in our free body. Okay, so we're showing a free body diagram here with normal force, force of gravity, which is equal to mg, force of kinetic friction, and I sacrificed a little bit of scale because of the picture being there, and our applied force. And I've resolved the applied force into a force applied on the y, which is the applied force times sine theta, and the force applied on the x, which is force applied times cosine theta. So far, so good. Now, with these problems, you have 3 equations that you can use. And you very often, starting off, don't know which of them you're going to end up substituting back into. This is also where it's often possible to solve this 2 different ways, maybe more different ways than that. But, certainly very often you can sub into this one or that one. So what I tend to do is I put down all 3 initially just to get them on paper so I see what I'm working with. So I've listed all 3 of my equations. Now I have the luxury right now of I'm working on doceri, so I can cut and paste and shrink and move. If you're working on just paper, I literally tend to jot these down across the top, right under my free body diagram, because it gives me a reminder of the 3 options I have. So, because we want acceleration, this one's actually pretty obvious. We know which one we're going to end up substituting back into. Which one has the acceleration? So here's what we've got listed. We have the equation for mu k. Mu k is equal to fk over fn. we have the sum of forces on the y-axis. And we know that sum of forces on the y here is equal to 0. The box is not spontaneously rising into the air nor sinking down into the earth. So all the forces on our y-axis accounted for, force of gravity, normal force, and force applied on the y. And I almost forgot force applied on the y. I don't know if you saw me sort of forget that. Good. And then on the x-axis, we know that on the x-axis, the mass times acceleration is not equal to 0. We're being asked for the acceleration. I mean, I suppose it could be, but it's a good bet it's not. And that ma is equal to the force of kinetic friction, which is opposing the force applied on the x-axis. If you were a betting person, which of those three equations do you think you're going to end up using to solve this? Sum of forces on the x. Reason being, this is the one that has ma. And we're looking for acceleration. So what we know is we're going to create expressions, and in this case we don't actually need all three of them. We're going to need to create an expression for the force of kinetic friction. We know normal force, and we know, so we have mass, we have force applied, and we have cosine theta. So we can do a substitution. What I'm going to do right now is I'm going to set aside my sum of forces on the y-axis. I'm not going to get rid of it yet. I'm not going to ignore it. I'm doing this cold and blind. I didn't practice by warming up and doing this morning. So I'm not sure I'm not going to use sum of forces on the y, but right now I think I don't need it. So I'm just going to kind of set it aside. And that is sort of the magic of Doseri. So I'm going to create an expression for Fk using my mu k. Okay, so I can just put that right in, huh? I just realized that I am going to need my sum of forces on the y. Do you see why? Why? Because my normal force is not, I mean, there's another force on the y-axis, so normal force is not just opposite gravity. So I'm going to basically do a double substitution. Ooh. Okay, so having realized that I spoke too soon and we do need our sum of forces on the y-axis, I need to rearrange to create an expression for Fn. So this is where it gets a little hairy and a little dangerous. This is hazardous territory. So if I want to create an expression for Fn, well, it's pretty easy. Fn, which is a force upward, is equal to Fg, which is a force downward, plus the force applied on the y-axis, which is also a force upward. What I have to be careful about, of course, is that that normal force and that applied force on the y are in opposition to one another. So remember what I said last week about, sine is a proxy for direction, and it's great. But in the real world, forces don't have a sign, they have magnitudes. And we know if they're in opposition, then you're looking at their difference, not their sum. So we're going to assign force of gravity a negative, and we do that pretty fluidly by just saying, oh, well, acceleration due to gravity is negative 9.81 meters per second squared. Bingo! Our F sub g is going to be a negative number automatically. All right. And I'll take this one step further and note that Fn is equal to mg plus force applied, and on the y this would be sine theta. All right, I have two expressions and I'm ready to blend them. Ah!
Yeah.
The negative of Fn. You're right. The negative of Fn would be mg, and this is where it does get dicey. It gets tricky. So whatever the magnitude of the normal force is, it is going to be opposite in direction to those other forces. Okay? So here, okay, so here's where the bone of contention comes in. We can either say, well, negative Fn equals mg plus force applied sine theta, or we can say Fn equals negative mg minus force applied sine theta. It's actually trickier to do it this way, because here you know, okay, well this has to be a negative number, so that makes it a positive. This has to be a positive number, so that makes it a negative. It's actually more to track. So let's go ahead and stick with this for right now.
It really just makes more sense to me.
Okay, and as you do more of these, you may change your approach. You're welcome to start out doing whatever seems most logical to you. I'll show you where all the pitfalls are, because I've fallen in every single one of them a couple hundred times. I'm well equipped to be a guide on the trip to pitfalls and these kind of problems, because, man, I've stepped in them all.
Appreciate the honesty.
No. Okay, is equal to the negative, oops, sorry. And actually, you know what? Looking at it, it works out to be the exact same darn thing. Times the negative of mg plus f applied sine theta. Let me shrink that. I didn't need to grab that. Equals fk. Now, here's another trip through the pitfall jungle. And let's go ahead and I suppose solve this real quickly for acceleration. Acceleration is going to be equal to fk plus f applied x divided by the mass of the box. Agreed? Okay. Here's the thing that you have to keep in mind. If we're using sine as a proxy for direction, looking at the little arrows that I've put over fk and f applied x, those are in opposing directions. So whatever the magnitude of that fk comes out to be, it has to be opposing the applied force. So you have to be looking at the difference between those two things. So their sum, in essence, should be less than the sum of the magnitudes. Okay? Whew, here we go. Okay, so what we have, bear with me as I read this to you, because I think the math language is important. Acceleration is equal to mu k times the negative of the quantity of mass times gravity plus force applied sine theta plus force applied cosine theta, all divided by the mass of the object. Okay, here comes the real fun. The algebra is pretty, it's beautiful, and it's art and all that, but, you know, it doesn't get us anywhere unless we actually have numbers, because this is physics, we care about the actual numbers. Okay, so I have it there with everything plugged in. Start your calculations and we'll come up with a raw number. And for the statement that was just made that the negatives are going to confuse me, that is the single hardest thing about this whole type of problems, is tracking sign and tracking what things are in opposition, and it gets worse as we start factoring more stuff out. Significantly worse.
So would the whole first quantity be negative?
Let's see. Let me highlight this to the best of my ability. So you're asking if this entire thing is negative?
No.
No. The
Like
whole
that whole...
bracket.
This whole bracket?
You had an arrow pointing up.
Yeah, that whole first thing.
That whole bracket. Well, that whole entire bracket is force of kinetic friction. So it's, well, I wouldn't put a negative in front of it. What I would do is remember that this entire thing has to be, I tend to put a little negative over it, a little positive over this, to remind myself that those things are in opposition, and that whatever their magnitudes are, you're looking for the difference of their magnitudes. Okay, so the correct acceleration for this is 0.12 meters per second squared. If you're not getting that, don't panic. Here's what I want you to consider. Now, on this problem, you are able to actually compute those intermediate quantities and get to the end, which is the thing that all of you want to do anyway. Well, my normal force is this. Well, my For static friction is this.
me.
That's
Do-
you.
do the numbers
Right.
first, then plug
Right.
in
Do
the
the numbers
numbers.
first, then plug them in. That's fine. You will get into problems in 4D where you literally cannot do that, and it's all substitution based. So,
Do you think the test will be a February? Shook.
I don't know. Yeah, probably. This is the 6th, I would imagine. So, get good at doing this. Get good at checking yourself by computing intermediates. And we will spend lots of time together working on strategies and tips and tricks and ways to avoid the potholes.
What's
Because
the best way to do these?
sadly, we're just going to spend a lot of time together.
That's,
We're going to spend a lot of
that's
time
the
together.
best way.
For some of them, it becomes the only way. So assigned is 4D, page 147, numbers 1 through 4. I'm not going to give you the worksheet yet, because that would just be craziness. That'd be cruel and unusual. So anyway, you can get started on 4D now. I'd like you to at least try one 4D problem. Don't be scared. You can do it. Pardon?